So far, we've looked at regular integrals over intervals, integrals over curves, and then integrals in two space, and then finally integrals over surfaces. Now we're going to talk. Now we're going to move to talking about integrals in three space. So let's start with a motivating problem here. So let's consider an object with some density, and we want to calculate the mass. Say we have some solid W, and say that solid has volume V, and we're measuring that volume in meters cubed. Say. And now, suppose the density of the solid is a constant, say rho, measured in kilograms per meter cubed. So the object has a constant density throughout. Well, in elementary physics, you learned that the mass of the object is the density times the volume. And you can see those units, kilograms per meter cubed times meters cubed, cancels out to give us kilograms. So we know from this that if we have an object with a constant density and we know its volume, then we can compute its mass. So what we want to talk about here is what happens if the density is not a constant anymore? What would we do then to calculate the mass? So for the first case, let's just consider we have a box here. We'll see later how we can handle other shapes, but for now, let's just start with a box. And we'll go ahead and assume this box does not necessarily have constant density. It might have constant density, but it might not. So let's suppose if I take a point x, y, z that's in the box, the density at that point is rho of x, y, z. You can see the density here depends upon the position in the box. So the density is allowed to change as you move to different positions in the box. So this is our question, then how can we calculate the mass of that box when the density can vary at every single point? So we're going to approach this the same way we've been approaching other problems in this class. When we have something like this, we're going to take that box, we're going to break it up into a bunch of small pieces, and then we'll assume the density is constant on each of the small pieces to get an approximation for the mass. And then as we've been doing, we'll let those pieces we broke it up into get smaller and smaller and smaller, and that'll give us a better and better approximation, and that'll end up becoming what our triple integral is. Okay, so let's suppose we have our box here like this, and we're going to break it up. So we're going to take each of the intervals from 0 to 1 in the x, the y, and the z coordinates, and we're going to break them into two subintervals. And we see here this will give us 8 boxes. So you have these 4 boxes in the front, and then you have 4 boxes in the back. So 8 total boxes we get out of breaking this up into smaller boxes. You can also think of that as each interval is broken up into 2 pieces, and there's 3 intervals, so 2 times 2 times 2, which gives us the 8. So the labeling in this case is a little bit more of a pain than it is in the previous cases. So we'll label each of these boxes with 3 subscripts here. So the first subscript corresponds to the x component. So we can see here in the x direction here, if we're in this first set of boxes, the first subscript is going to be 0. If we're in the second set of boxes, the subscript will be 1. Then similarly in the z direction is the third one. So if we're in the bottom row here, our z index is 0, and the top row our z index is 1. And then similarly if we were going back in the y direction. So this gives us a labeling for each one of our boxes. Now for each of the boxes, we're going to pick a point inside that box. We'll call it xi star, yj star, zk star. And it can be any point in the box. It can be on the edge of the box as well. It just has to be somewhat in the box. So then we're going to, the density is not necessarily constant on these boxes. It can change in the box. But we're going to assume that it's a decent approximation, since we've split the box up, to go ahead and approximate the density as constant based upon our chosen point in the box. Now we know we picked a simple situation where we're working with just boxes here, so we can calculate the volume pretty easily. It's just delta x, delta y, delta z. And since I split each of those intervals up into 2 pieces, each one has delta x, delta y, delta z is each 1/2. So we get 1/8 for the boxes, which makes sense because there's 8 boxes splitting up a box of volume 1, so each one better have volume 1/8. So then if I want to approximate the mass, all I'm doing is I'm taking, for each of the little boxes, I take the density of that box that I'm approximating, multiply it by the volume. So this little part here is approximating the mass of each box, and then I add up all of those boxes. And we can go ahead and replace this volume with the 1/8 if we want. But the idea is this piece on the inside is approximating the mass of each of those Wijks, and then we add up all of those masses to approximate the total mass. This should look familiar to things we have done before, just not with volumes necessarily. So let's look at an example. So let's suppose our density function is just x times y times z. So let's just pick some points. Like I said, you can pick anything you like as long as it's in the box. So the first part of the interval is from 0 to 1/2. So we pick x0 star to be 0, y0 star to be 1/2. That's at the right edge point. And then z0 star to be 0. And then the second half of the intervals is from 1/2 to 1. So we pick x1 star to be 3/4, right in the middle, y1 star to be 1, so we're at the right edge, and z1 star to be 1/2, so that's at the left edge of the interval. And then we can just go ahead and fill this in. This is a big old giant mess here, but all we're doing is we're taking these points. This is x0, y0, z0, and then the volume. And then I've got x0, I've got y0, and I've got z1, and so on all the way through. And then we just plug that into the function x, y, z, and we get these values. So anytime there's a 0, of course, since it's x times y times z, if any of the entries are 0, that's just going to give me a 0 for the function. So we're only left with two of them where it's not 0. So this one has no zeros, and this one has no zeros. So that's these two pieces. And that just gives us a 9/128 for our approximate mass. So as I said before, as usual, what we do is to get a better and better approximation, we just increase the number of pieces that we break the object up into. So more and more boxes will give us a better and better approximation, because the smaller the little sub boxes, the better our approximation that the density is constant on that sub box. So for instance, here's breaking it up into more boxes. So we have lots of boxes here for this piece. I think there's maybe 10. Yeah, there's 10 in each direction in this case. So we've broken this box up into 1,000 boxes now. So how are we going to get integrals out of this? The same way as we normally would. So we let those delta x, delta y, and delta z all go to 0, which means we're increasing the number of boxes bigger and more sub boxes. So as usual, we have this kind of nasty thing over here. But remember, this part here is the approximate mass of one of the small boxes. When I add the sums on, I'm adding up all of those approximate masses. And then this limit is saying let those boxes get smaller and smaller and smaller. And so this thing here will give me my exact mass. And we denote this thing here, this giant mess on the right-hand side. That's how we define this integral on the left-hand side. So we don't know what this thing is until we know this. So this over here is equal to this. So in our particular case, we can figure out what the regions are. So each of the boxes is going to go from 0 to 1, so we get a triple integral here. And that's how we would calculate this volume for our box. Now, as we saw in two-dimensional integrals, obviously we don't want to have to just stick with boxes or squares. We want more general regions. So same thing we did in the other cases. The boxes don't necessarily match up perfect for a general region, but if you let the boxes get smaller and smaller and smaller, it becomes a better fit, and you can take only the boxes that are inside the region to kind of fill it out, and that'll give us a way to deal with more general regions. And what we'll see when we start setting these up in class to actually evaluate some of these integrals is just like since we had regions in R2 that were quite complicated to set up the limits of integration for, we're going to have the same thing here for regions in 3 space. In this case, it can be even trickier than in the 2 space to set up the limits properly, but we'll go ahead and stick for the most part to fairly simple regions that we can set up integrals for. So that's what we'll be doing going forward.